minutes before ending? Just 30. Okay. Just tell me 5. Okay. First of all, I would like to thank the organizers for inviting me to be here again in Sao Paulo. It's a great city. And yeah, I am a network scientist. My name is Javier Buldú, and I am in Madrid. I work at the Center for Biomedical Technology and also at Universidad Rey Juan Carlos. And today I'm going to talk about what happens when you have one network, you have another network, and you connect these two networks between them. In principle, you can connect them at random, just placing links wherever you want. But we realize that the place where you put the links is crucial in the processes that are occurring in these two networks. And I'm going to show you an example to motivate this study. So everybody knows in Madrid that in Madrid we have the best metro network in the world. And I'm going to prove it because I have the numbers. This is the proof that we have the best metro in the world. This is a survey a journal made asking just what is the best metro in the world. Okay? And you can see here that you have London, it is around 8%, Paris 3%, New York 2% of the people. Taipei, I don't know who have been in the metro of Taipei, but 2%, and Madrid 60%. So this is the proof that we have the best metro in the world. So we are so proud about our network of connections that the metro has. Okay? I have another proof for the people in Sao Paulo. I realized yesterday that there was a meeting in Madrid where the representatives of 19 of the 19 largest metro networks in the world, they met together, and the one from Sao Paulo, Paulo Labate, said that the metro of Madrid is fantastic, it has many lines, they arrive to all the city, and in addition, he adds, in Sao Paulo, we travel more packed than in Madrid. This is something I realized when taking the metro, especially at the end of the day. So, okay, we have a great metro network. We are so proud of it. And even more, the metro network is connected to other networks. It's connected to the subway, to the suburban train network. It is connected to the tram network. And it is also connected to the bus network. So we have different networks that are connected between them. And each network has its own identity. So it makes sense to analyze the metro network, but it also makes sense to analyze, I don't know, the suburban train network. But what it really makes sense is to analyze all of them together because they are sharing passengers. Okay? And they have common connections. They have stations where they share the people. And that's good for all networks. I mean, it's good to share, to have a common connection between the suburban train network and the metro. Because, for example, if I were the responsible of the metro in Madrid, I would like to receive more passengers. So if I can get passengers from the suburban train network, that's great for me. Because I can go to the major and ask for a larger budget. Okay? But at the same time, people can come to my network, but they can leave. They can decide to go to use just the other networks. And then I'm going to lose people. So, I mean, it's good to be connected. For sure, it's good to all the people. But it's clear that I am in a kind of, if I am a network, I am in a kind of competition with other networks. It's good to be connected with them, but I would like to know if I am gaining or not, and who is gaining more. Is the metro network gaining from the connection to the suburban train network, or it is the suburban train network the one that is gaining more? So this is the kind of questions we try to answer. Having more people in your network, more passengers. In this case, I mean, you can define the outcome in many different ways, as I will explain later. And yeah, that's good, but sometimes it's bad because in 2010, we had what we called a savage strike, where the metro, people working at the metro decided not to work one day to increase their salaries, and they decided not to respect the minimum services. So the metro network completely collapsed, but also the bus network collapsed, the tram network collapsed, the whole city was collapsed. All networks went down, okay? So as you can see, it is important, these connections between them. What happens in one network is going to influence the other networks, and this is the kind of things that we want to analyze. So to be more specific, I will treat the problem of having one network with what is a group of nodes, whatever it is, with a certain identity, and having another one. And I want to study what happens when I connect them, when I introduce links between them, and how I'm going to introduce them. You can do this in many different ways. So to be more specific, I'm going to explain, to focus the problem in the kind of connections we are going to introduce between two networks. So at the beginning, I will depart from having two independent networks, one that I will call the strong network, and another one that I will call the weak network. The strong network is a network, as a rule of thumb, with more nodes and links. Okay? So the network with more nodes and links will be the strong network for me. And the one with less will be the weak network. This is a rule of thumb, okay? In fact, I define the strong network as the one who has the largest eigenvalue at its adjacency matrix, which is in turn related with the number of nodes and links and more things, but okay, we can go to the details later. So the one that has the largest eigenvalue is the strong one, and the other one is the weak one. Inside each network, I can identify what are the most important nodes, and there are many different ways of doing it. For example, here I have a node with a lot of links. It is for sure that it's going to be more important than this one that has only one link. One way of computing the importance of a node is using the eigenvector centrality. Okay? I will explain more or less in the next slide what it's about. But the thing here is that I want to show you that I have important nodes here, which I will call central nodes, and less important, let's call it less important nodes, which I will call them peripheral nodes. So I have C nodes and I have P nodes. And the connection can be, if I create just one link between them, I can create a CC connection, so a central, a hub with a hub, a peripheral, less important with a less important node, and also CP or PC. Note that it is not the same to connect the strong one, the peripheral node of the strong network with the hub of the weak, or the peripheral node of the weak with the hub of the strong. So CP, PC is not exactly the same. So more or less it's clear what I can do. So I have two networks, one is important, one less important. I connect them through one link, okay? And I can do it in different ways. I told you I was going to say something about the eigenvector centrality. Yes?
One question. You don't need any other relation between the networks, but the eigenvalue. That's the only.
This is the way to decide what is the strong network.
No other condition.
No. I mean, if you change something in the network, the eigenvalue is going to change somehow. So the eigenvector centrality is a measure of importance. Okay? And how does it work? As a simple measure of importance, you can use, for example, the number of links. The node with a higher number of links is the most important. Okay? But this is a more sophisticated measure. How does it work? There are different ways of interpreting this measure, but I think the one I'm going to tell you now is the simplest. You have a network, okay? And you assign an importance to each node randomly, at random, okay? And then you begin to iterate. You do an iteration process, and you reassign the importance of the nodes at each step. How are you going to reassign the importance of each node? Very simple. You take the importance of the neighbors. So you count for the importance of the neighbors, and then this is your new importance. Do you understand more or less? At the beginning, you distribute randomly the importance, and you take at each step one node and assume the importance of the neighbors. Okay? And you do it the first step. So if I am a hub, I will assume the importance of a lot of nodes. and I got it. Then I do it again. But note that my importance has changed, but the importance of the other nodes has also changed. So I have to recalculate the importance of all nodes. And I do it again. It's suffering. The camera is suffering. Okay. Okay. So I do it again and again and again and again and again. So if I do it again to infinity, I arrive to one value that you can get it from the eigenvector associated to the largest eigenvalue of the connectivity matrix. And this value is the eigenvector centrality. Do you understand more or less what I said? Note that this measure takes into account, it's related to the number of links you have, but also is related to how important are the nodes that are connected to you. So it's a more sophisticated measure of importance of a node in a network. So I can obtain the centrality, the eigenvector centrality of all nodes, and assign a value to each node. Okay. So as I have explained, this is an iterative process, and it is very related to any dynamical process that occurs in this network that you can define with a let's say transition matrix M. So if the state of all nodes at time t plus 1 can be explained as a state of the nodes at time t multiplied by a transition matrix, if you iterate this process to infinity, the final distribution, the final value of this variable n, whatever it is also the eigenvector centrality. So it is related, for example, with the movement of agents. What is the probability of finding an agent when time goes to infinity? So this eigenvector centrality is a very nice metric that tells you the importance, but also it has a certain interplay with the dynamics occurring in the network. So I explained that because I'm going to use the eigenvector centrality later. So let's go to analyze a competition between two networks. If I want to analyze how can I compete and what are the best strategies, I need to define a target. What do I want to optimize? And in this case, my target would be my target as a network. So I'm just thinking I am a network, not a node. So the target will be to increase the importance that I acquire in my network. And this importance is very simple to measure. Just I will sum the importance of my nodes. I compute the eigenvector centrality of my nodes, and then the sum of all of them will be the importance accumulated by this network. And I will also have the importance accumulated by the other network. Okay? So this importance is obtained from the eigenvector centrality, the first eigenvector, the eigenvector associated to the largest eigenvalue of the network of networks. So I have one network here, another network here. I connect them. I compute the eigenvector of the whole network of networks, and I see what is the centrality accumulated by the nodes in A, just assuming the eigenvector centrality of its nodes, and then the rest will go to B. As you can see, CB is defined by 1 minus CA. So the more importance network A has, the less importance network B has. So they are in a competition. Let me show you an example. Here I have two networks. They have 1,000 nodes and 2,000 links. Okay? They are heterogeneous. They are created with the Barabasi-Albert model, and they are very similar. But network A has a largest eigenvalue. So when I compare the largest eigenvalue of these two networks, A is the strong one. Then I number the nodes of each network according to the centrality. So node 1, it is the most important. Node 2, the second most important, up to 1,000. Okay? And then I am going to connect all these two networks in all possible configurations. Okay? So here I have plotted what is the centrality accumulated by network A. 1,1 here is the centrality accumulated connecting the hubs. And 1,000, 1,000 is the centrality accumulated connecting the most peripheral nodes. And as you can see, if I connect the hubs, I acquire around 0.55. And if I connect the peripheral nodes, I am very close to 1. Okay? So just placing the link at the right position, I will get close to the double of centrality. So as you can see, it is very important to select the adequate place. And of course, CB is the opposite. So here CB will be close to 0.4, and here will be close to 0. Okay? So this is the problem that I'm going to study, and what we did is to analyze the structure of the network of networks. When I take one network, I take the other one, I connect them, I compute the eigenvector centrality, the eigenvector associated to the largest eigenvalue. I am going to compute it and see how it is split between these two networks. So what we do is to construct this network of networks. I have the network A, I have the network B, and this is the connector matrix. The connector matrix contains the links between these two networks. And I can have one, but I can have many. The easiest case is one. But you can extend that to many links. Okay? So there are three vectors that are very important. The first one is UT1. UT1 is the eigenvector centrality of the whole network of networks. UA1 is the centrality just of network A before connecting. The eigenvector centrality before connecting. And it is a vector that it has certain values up to the number of nodes I have in A, and then the rest is 0. Okay? Because it's before connecting. UB1 is the same but for B. So I have zeros in the nodes corresponding to the nodes of network A, and then here I have the values before connecting. So it is the importance of the nodes before connecting. UB1 has the importance of the nodes of B before connecting. UA1 has the importance of the nodes of in A before connecting, and UT1 has the distribution, the final distribution. This is what I want to obtain. So we analyzed this case and obtained this formula here. I'm not going into details, but we can discuss it later if you want. And we obtained this formula that it is very nice and helpful to understand what do you have to do if you are a network. So here, what you have is this is the eigenvector of the network of networks. It's what you are going to split. And you are going to split this between, you have certain values here, and this goes to CA. And this goes to CB. So these are the nodes in A, these are the nodes in B, okay? So this is a relation between the initial centrality of both networks in this way. No, it's the opposite, sorry. I have to write it because I want to show you what happens if you increase or decrease one thing. Okay, so as you can see, the final distribution of centralities is related to the initial distribution of centralities of A and B. Okay? It's related to them. It's a combination of this. This is an approximation. Okay? And, but it is highly dependent on this term. So if this term is very low, I have this. And this is the centrality of A. So UT is very close to UA, so everything goes to A. So A wins. If this is very high, things are moving to UB. Okay? So I get more centrality here, and CB is increased, and B wins. Okay? So this term is very important. And what is this term? Look, here I have the connections. This is the matrix of connections, and these are the initial centrality. So this tells you, this contains the centrality, the initial centrality of the nodes, and also how many nodes I am connecting. The number of links is here. Okay? And this is the centrality, the initial centrality of the nodes. The higher this value is, the better for B. So the more links I introduce, the better for B. The more important the connector nodes are, the better for B. So the weak network, B, the weak network, wants to be connected to the strong network through the hubs. Okay? But A wants the opposite, wants to be connected with the nodes with less importance. And what about this? This is the difference of largest eigenvalues. So the closer, if B decreases this value, if B has a very low value, this value is going to be high. So it's going to reduce this term here, and everything is going to A. So the more separate, the more difference they are between these two networks, is going to be good for the strong network. Okay? The strong network wants more differences between. So this gives you the strategies that you have to play to win. And you can summarize in these 4 strategies. If you are a strong network, you should connect through the peripheral nodes. If you are a weak network, you should connect through the central nodes. The higher the number of interconnections, the better for the weak network. And increasing the largest eigenvalue of a network increases its centrality. So if you're a network, you have to increase your centrality. That's good. A wants to increase the centrality, so the difference between them is higher. And B wants to increase the centrality, so the difference is also is closer, and then this term is going to increase. Let me show you some simulations. How much time do I have? 10 minutes?
10 minutes.
Okay. So here you have a very simple simulation. Also, we did some analytics. We have a star network here. A star network, in a star network, you have a center and the leaves. So we have a node here at the center, and the leaves are here, just the green one. Okay. This network has 100 nodes, and we have network A that has a variable number of leaves, and we are going to increase this number of leaves. And this is the centrality accumulated by A. Okay? And we are going to increase the number of leaves. So we are adding nodes here. We are going to add nodes and nodes and nodes and nodes and see what happens. So this is CA calculated through a PP connection, so through a peripheral connection, and through a CC connection, the hubs. So I begin to add nodes, and I see this. If I am connected through the hubs, I see how I am beginning to gain centrality. So around here, around 100, it makes sense. I overcome B, and then I increase and increase, and I get more. Okay? What happens if the connection is PP? Well, I am not winning that much, and suddenly I overcome the other one, and I have a very sharp increase, and then I overcome the other one. So the first thing that you can see here is that size matters. It's important. Okay? In fact, it is not the number of nodes. It is the value of the largest eigenvalue, that it is related with the number of nodes. And once you overcome the other network, you are going to win. But it is very important the way you are connected. If you are connected through peripheral nodes, you will have sharper transitions. If you are connected through the central nodes, the transition will be smoother. So this is something I didn't know, we didn't know, or I didn't know. And this is another example where here I have network A, whatever it is, with a certain eigenvalue, largest eigenvalue, 6.76. And then I have network B. And network B cannot increase the number of nodes or links. Okay? I have a certain restriction, and I cannot increase it. But I can change the connections. So I can reorganize. So we introduce here a genetic algorithm that basically changed one link and accepted the link, the change, if it increased the largest eigenvalue. So we were we began to iterate, and observed how increasing the eigenvalue, this network could reorganize and overcome the other one. Okay? Again, we observed that CC connections are smoother, and PP connections lead to sharper transitions. And finally, we realized that once you can identify what is the best strategy for you and your enemy, you can characterize what is happening in real networks. Okay? And I'm going to show you with an example. This is a network of interactions between dolphins. It was obtained by Luzo, a biologist. And with Newman, they realized, they were tracking how dolphins were relating to each other, okay, following them through GPS. And they constructed a network of connections between them, and they realized that there were two communities of dolphins. This one that is larger than the other one, and this one that is smaller. There were around 60 dolphins, and I think this one has like 40 dolphins, and this one has around 20. So you have the interactions between inside the community, inside the other community, and you could count a number of links between them. Okay? So this is the real network, and you can calculate what is the distribution of centrality accumulated at these two networks, and we can see that this one, the strong one, is winning. It retains more centrality than the other. The centrality is proportional to the size of the nodes here. Okay? So what you can do is the following. You can say, okay, what would happen if I change these links? I test all possible configurations, and I go to the best strategy for the weak network. What would happen? So I can estimate what is the best strategy for the weak network. So I can calculate it. In the best strategy for the weak network acquires around 30% of the centrality. Okay? And the other one around 70%. Note that maybe you cannot overcome the strong one because you are weak, but at least you can retain more centrality than in this case. We can do the same for the strong one. Okay? So we have the optimal strategies for the weak and the optimal strategies for the strong. And using these two values, we can define the competition parameter, omega, that is normalized here. It's a linear normalization. So omega is 1 if you are in the case where that is the best case for the strong network, and -1 if you are in the case that it is the best case for the weak network. 0 indicates that it is a balance of a strategy. None of them is playing the best, as close to the best strategy. So here in this case, we had 0.7. That means that they are connected in a situation that is close to the optimal case of the strong network. And you can use this metric to see what is happening in real networks, if they are connected in the optimal way for the weak or for the strong network.
5 minutes.
5 minutes, perfect. So yeah, this is my last slide. And I'm going to just mention 4 different applications of this idea, because I mean, at the end, what I want you is to have the idea that networks the connection between networks are crucial in things that are happening in networks, okay? So maybe you can apply to different problems, not exactly centrality. Whatever is your outcome, probably you can define the problem in a different way, but you have to think about how to connect them. So I would like to mention 4 different works that we work, and one that is still under revision. Here we were investigating what happens if you have several networks. So imagine this is a network with connections. This is a network with connections here, and this is another one. So I have network A, B, and C. Okay? If I am this network, I can create a link to this network or to this network. Maybe I can connect to this one or to this one. And I want to choose. I have one link to connect, and I want to choose. Should I connect to the strong one or to the weak one? It depends. Okay? It depends on the eigenvalues. And it depends on the nodes that I am using to connect. So sometimes it's good to connect to the strong one, but sometimes it's good that the 2 weak networks connect between them, because they are going to overcome the other one. So what we did is to study the Nash equilibrium. We let networks to change the links until they arrived. I mean, this one can create one link here, this one here, or no, then changes the network. And finally, you arrive to an equilibrium where changing the link is bad for any network. And this is the Nash equilibrium. So you can study the Nash equilibrium of this system, and we realize that the weak networks have more power than they think, okay? Because connecting with networks in certain scenarios can lead to the overcome of the strong one. So this is about the Nash equilibrium. Another thing is what happens out of the equilibrium, because I am just always talking about what happens at the end. But imagine that, as I explained, this centrality, it takes time to renormalize. If you are studying, for example, moving agents, it takes time to agents to move from one network to the other. And we realized that sometimes using a strategy that at infinity is bad for you, it could be good. Okay? And here you have an example. This is do you remember that the strong networks want to be connected through CC connections? And PP connections through the peripheral nodes. And CC connections are good for the weak networks. CC connections are very efficient, and because they are connecting the hubs. Okay. So if I measure the centrality accumulated by, or the number of agents moving through a network A, and imagine that the starting point is having everything in network B, and I compute that on time. Look, this is the PP connection, this one here, and it's the best one for the network A. But it takes time. It takes time because you are connecting networks through the peripheral nodes. So look, I have to wait until here it begins to increase and finally arrive to 1, what is the best case for me. If I use the CC, I have this. It increases faster, and I stay here. Okay? So around 50%. That's not very good for me at the end. Okay? But what happens if I cannot arrive to infinity? So suddenly something happens and the connection between the two networks is broken. So if the connection is broken here, the CC strategy is better for the strong network instead of the PP because it didn't have time. So what is the best thing? To combine strategies. So use the CC strategy up to here, and here changing to the PP strategy. So you use one, and then you change the other one. And this is what we studied in this paper that is under revision right now. In brain networks, there's a way of computing or trying to understand what is the importance of nodes in a functional network. And with Mario Chavez, we analyze how this importance is distributed between hemispheres, where the two networks here are left and right hemispheres. And it allows you to understand if they are competing or not, and what is the importance of the connector links between hemispheres. And finally, this is not competition, but cooperation. We were thinking about a cooperation situation. Not competition, cooperation. So we thought, okay, let's go to synchronization. Imagine that I have one network here of dynamical systems, another one here, and I want to synchronize the two networks. Okay? Look, this is a very simple simulation. This is the synchronization error of the oscillators of the two networks, and they are not connected. At the beginning, they are isolated. Of course, the synchronization error is not 0 because they are not connected. So maybe here I am synchronized, maybe here I am synchronized, but I have a synchronization error between nodes here and nodes here. I don't have exchange of information. So I have this error here that evolves in time, and at this point, I connect them through a peripheral link. And the synchronization error decreases, but fluctuates also and doesn't go to 0. Here, at this point, I connect them change the peripheral connection, I connect them through the hubs, and suddenly I see that they get synchronized. So choosing the adequate connector link is going to tell you if your network of networks is going to synchronize or not. And this is what we studied here. And that's all what I wanted to say. Be careful and pay attention to the way networks are connected. Thank you very much.
Thank you very much, Javier. Questions? Stefano?
No, Stefano, no.
Yeah.
Stefano.
No, it's not a question, it's an observation in the sense that there are many, the definition of centrality is not unique. There are many centralities. There is node centrality, eigenvector centrality, page ranking centrality, between the centrality. And this is because each one of these centrality has a different role depending on the process, on the dynamical process you are studying. So a node can be very important for a process and not important for another process. Now, you have shown that in eigenvector centrality, you have this redistribution when you connect the network. But eigenvector centrality is mostly done for linear processes. Now, how are you sure that the same redistribution happens when you study, for example, synchronization, as you said, brain, and so on and so forth, which usually are not linear processes, and maybe they need a redistribution of other kinds of centralities?
Yeah, it changes completely. If you change the target, everything changes. For example, in the case of synchronization, we had to study the Laplacian matrix and the properties of the Laplacian matrix, not the eigenvector centrality distribution. So we had to focus to another completely thing. If we wanted to focus on the between the centrality, then the output is another one. and you have to do another different thing. So it depends on the thing that you are studying. In this case, we thought that the eigenvector centrality was very useful because it's related, as you say, with certain linear dynamical processes. But for example, you can use it to describe SI epidemics, or with the model SI. SIR also are related to this. So it has applications to spreading, for example. Also the time to synchronize Kuramoto's, it goes with the inverse of the Laplacian. So it has certain connections to certain things. But if you want to study a different problem, you have to define your target and work towards that and analyze what happens. Maybe the strategies are different. If you want to promote the betweenness, I don't know, we didn't study that. We can do it if you want.
Thank you, Javier. Very nice talk. I want to make a comment and a question. Like a comment, probably you know as well about the Gershgoring theorem. That bounds the eigenvalues of the Laplacian matrix, and especially it's useful for the highest eigenvalue. And that one is bounded between the highest degree as well, so basically the heuristic.
But comment. Are you talking about the Laplacian matrix?
Yes. And you can use as well for normalized one. But yeah, in any case, I mean, the comment is regarding that you have a heuristic way to predict which connections you should do in terms of, well, just increasing the highest degree. No, that should increase the
yeah, I mean, in this case, the Laplacian is not relevant because we are just working with the adjacency matrix or the transition matrix. Mm-hmm. Okay? The Laplacian is important in the case of synchronization. In that case, for sure, you have to pay attention to that. But the change is not that simple. I mean, you have a limit, in fact. This theorem tells you the limit.
The upper bound, yes.
Yeah, the upper bound.
But the lower bound is k plus 1.
Yeah, but I mean, it is not that simple. I mean, it is not that, okay, I am going to increase the
My short question was about scalability, because eigenvectors usually scale quite high.
Yeah, but this is something we didn't investigate it. Yeah, but probably we could do it, yeah.
Okay, any other question? I have one short one. I mean, in these cases, you have more than two networks that you want to compare. Have you looked if the most efficient way to connect at every step follow any ultrametricity or something like that? I mean, because I mean, there could be, I don't know, because that will define different distances, and it could be that a particular system follows something like that. Because I have seen it in some smaller networks where in synchronization I have seen they follow that.
I don't know. I mean, we didn't check that.
You never checked that?
No, the thing is that we believe that you can do many things. Uh-huh. Once you realize that it is not just throwing links at random.
Yeah.
So
No, that's why. That's why, because you could, I'm sorry, so because you could have defined something like that instead of I mean, you're comparing eigenvalues. You could compare states in a different way. So I don't know. I'm just asking.
Yeah, yes, I mean, I think there are many things to be done still.
Okay. Well, Nivedita has another question. Let's see.
Thank you. I just wanted to know how you're solving the problem that you started off with. That means the several bus and the tram. How are you solving it?
We didn't
from
solve
your
it.
analysis?
No, we didn't solve it. It was just to introduce the motivation of the problem, but we didn't solve it. Yeah, but in principle, if you have a model that fits.
But you're making some steps towards solving it. So what is the step that you've made in solving it?
But are you talking about the movement of passengers through the networks?
No, the collapse of the. You want to.
Yeah. No. It was.
To prevent that.
Right? Yeah. We want to prevent that.
What is the movement towards solving that problem?
But
by doing all this?
I don't think you can do it directly using this. It was just the motivation and just to make you realize that the connection between networks are important. But we don't want to, for example, simulate the collapse of a power grid or something like this. Probably there you would need more sophisticated models that related with the capability of each node and I don't know, the probability of failure and these things. And I don't know if they can be translated into a transition matrix that can be treated in this way. But you can think about it and try to find similarities in the way of solving the problem, of detecting. I mean, you can do simulations, just testing what happens if you connect one node, the other, if you have a model, a dynamical model, whatever it is in your nodes. So this is why I say that there are many, many things to do still, to apply to your particular model and see what you have to maximize instead of the eigenvector centrality.
Okay. Well, we can discuss later or at lunchtime. So we go to lunch now. Thank you very much to all the speakers.
No,